Hi. So here I'm going to be solving part 2 of our exam 1 given to us in transport 2. And in this part of the problem, we are going to be trying to find and graph the mole fractions and the molar fluxes of the components in the Stefan tube throughout the system as it passes through the total system in the tube. And so, if you've watched through part 1, we know really how we've gotten so far and where a lot of the stuff has already come through, so I've already typed it out just to save a little time. Before we even really start and go through all the stuff that's given to us to start the problem, we have to go through and import some functions through some of the libraries that are offered in Python in order to help us solve this. So we imported numpy as NP, which is pretty much numerical Python. It allows us to do numerical calculations. We imported solve underscore IVP, which allows us to solve initial value problems, and that's under the SciPy integrate library. And so that allows us to do that. We also, we also imported roots. So that allows us to pretty much, it's a root solver. So that allows us to solve roots and give us our mole fractions later down the road when we need to get that. And that's from the SciPy optimize library. So it's an optimized function. Plotly.subplots makes subplots. That allows us to pretty much make graphs within our code. So we can go through and actually plots graphs, and we'll show that later when we're graphing our concentrations and mole fractions with respect to the distance traveled in the tube. And we are also importing plotly.graph underscore objects, which pretty much just allows us to graph multiple mole fractions values on our graphs, and it will just make things a lot easier down the line. So, just turn that up. And now that we've gone through that, we can go through and explain really what was given to us in the problem. So we were given all of this, most of this stuff through here. So pressure, temperature, gas constant, concentration we can find from pressure over the gas constant times temperature, and delta is 0.24 meters. We were also given the Maxwell-Stefan diffusivity constants for the components that are in the system, which were also supplied to us, given here. We were also supplied the initial mole fractions for the components in the system here, where I believe this is acetone is 0.319 and methanol is 0.528. Here we identified and created some new variables to really condense and reduce the complexity of having to type out D12 delta C, all this stuff each time it comes up. So it makes it just a lot easier to code and reduces a headache for a ton, really. And the last thing here that we have is our initial guesses. And this was also found in part 1, and I'm just going to assume that you know how we got these, as it was through scaling and order of magnitude. You can go through and watch part 1 if you don't know where these came from. But anyway, now after we've gone through this, we can start going through and really working out the code. And so I'm going to go down here and make a note, because we know that we're going to have to solve an IVP of some sort at some point in time here. And so not really worrying about that right now. That's just something we're going to come through after we define some of our functions that we're about to use. One of them being we are going to define the Maxwell-Stefan equation that we will use, and this will be in terms of eta and y, and this will also be from when eta is from 0 to 1. And now that we have this pretty much in there, we will define our new values, where y1 is equal to the first value in the array, because we do have 3 values of y that we are trying to keep track of throughout the whole process. We're just going to keep them in an array and store it to make it cleaner. So y1 is the first value in the array. Arrays are started at 0. Y2 is going to be the second value in the array, depicted as y of 1. But instead of y3 being the second value in the array, it's actually going to be 1 minus y1 minus y2. And this is just so that we can keep track of all of these values over time, pretty much. Because of this, the mole fractions will always be the summation, and the summation will equal 1. So y3 will always just be 1 minus the mole fractions of y1 and y2. And so now that we're here, we really want to return the Stefan Maxwell values. And this is where it's always fun for me because I struggle with typing this out. But, sorry. We want to return an array, which is why we identified that as part of the array there. And so we want to return NumPy.array, which is a numerical Python array, where it's going to really solve us. I'm sorry, I'm looking over to the side just to see how much time it's really taking me to work this out. So it's going to be y1 multiplied by n2 minus y2 multiplied by n1 divided by f12, and this is going to be minus y3 multiplied by n1, I believe. Yes, y3 multiplied by n1 divided by f13. And that is going to be the first value in this equation. I need to add in this and this. Just to clean that up a little bit, okay. And then going into the second value, it's going to be y2 multiplied by n1 minus y1 multiplied by n2. This will be divided by, I need to add in a parenthesis. This will be divided by f12 as well. And minus, this will be y3 times n2 divided by f23. And so that is our entire return of what we want, and that should be the Maxwell-Stefan equation that we will be wanting to receive, give us the values of the molar fluxes that we would like. And so from here, if we would like to run this, let's set up our solve IVP first. So when we're setting up a solve IVP, we need to really identify which function we are wanting to solve. So we want to solve our Maxwell-Stefan equation. So that'll be what we want to solve. And then we want to solve the range of the time. So we want to solve from the time that eta is from 0 to 1, which is pretty much the length of the tube at this time because of the factor that we scaled from. And so that's going to be from 0 to 1. The next thing we need to do is input our initial values, which will be y1i and y2i. Oops. So the next is the method that we will use. The method that we will use here is the Redau method. Clean this up a little bit. Redau. I'm not really too familiar with how this works, but it's the method used to solve the equation, the initial value problem. And because of this, I just know that my professor prefers it, so I'm going to continue to use it. That's really the only reason why. And then the last thing that we will need here is the dense output equal to true. And so really, I think I added 1, 2, yeah, I have 1 too many parentheses. So really what that allows us to do is just allow us to call back to it as a function later down the line. And so if we tried to solve this, yeah, it did not work out very pretty at all. And this is just because N1 and N2 are not defined here. So that's the main reason why that this is not working. It's outputting a value, but it's not actually, what am I trying to say here? It's not working correctly, is what I'm really trying to say. And so what we want to do here is we want to define another equation. And this equation is going to be our mole flux solver. And this is going to be in terms of n, which will help us just really define these values of n1 and n2 that we need. So n1 is going to be equal to the n array value of the first one. And n2 is going to be equal to n array value 1. And so this really just sets the equations, the new n values, identifying them and trying to set them up. And so what we really want to do here is, I'm just going to use a temporary variable here, and set this equal to res. And what we want to do is we want to return res solution 1. Indentation. Alright, add some indentation, see if this fixes it. Return outside function, syntax return. So it looks like I'm having some syntax error here. Is it because of this bracket? Don't use brackets. Huh. What is wrong with this? It's not brackets, I don't think then. Is it a potential? What is wrong with this? Because we have the embedded code, return mp.array, y1 times n2 minus y2 n1 over f1 2 minus y3 times f1. I'm not sure why this is not working. Oh, it might be. Hold on 1 second. Yep, there we go. Sorry about that. That was just because it was not embedded. It needed to be embedded into that second equate function because it wasn't being called to return the actual value. That was the issue. Took me a second. But really, once we're here, we pretty much worked through and solved this part of the equation. And so now we can go through and solve the root finder. And so we want to set up to find the molar fluxes here. Now that we already have found the molar fluxes, we're going to return those values. So we want to create that root equation, which will be root, and the equation we want to solve, which is the mole flux solver in terms of N1I and N2I. And so I want to set this equal to, now just for reference, I'm going to make this equal to the mole flux. And so this should work. Nope, of course not. So it can be lower. Yep, that just needs to be lowercase. So just to make sure this works, mf.x. Yep. Okay, so that actually ends up showing us our array that we currently have. So that just tells me that it's working right, and I don't really have any issues right now. So this returns the solves value at eta equal to 1 because the mole fractions are going to be, they should be 0, but they're probably going to be just a very, very small number close to 0. So I'm going to get rid of this just to clear up some space. And let's go on to the next part here. And so now that we have this, we can go through and assign our, pretty much just assign our new values for N1 and N2. So N1 is going to be the value of the first value of the, whoops, that needs to be capitalized. And yeah, MF could be a curse word, but let's just, let's go with mole flux for right now. NF.x, and that is going to be the first value in that array, and N2 is going to be the second value in that array. Messed up the capitalized again. And so now that we have this, we can really just go through and solve the IBP for a value that we have provided. So we have these new values for N1 and N2. So what we can really do to make this a little easier is we can go up here and copy and paste the Maxwell-Stefan equation down here. But instead of this being res, this is actually going to give us the mole fractions of what we're trying to solve here. And so the mole fraction, setting that equal up to the solve IVP, that pretty much allows us to get values of the mole fraction with any given time for the values of N1 and N2. And so now we have those actual values of N1 and N2. I'm going to go through and I just want to check to make sure this works. Oop. Fraction, oh, spelled that wrong. Fraction dot x. No, sorry, wrong thing. Solution 1. And that's going to solve it for when eta equals 1. And what's new? There's an indentation error. Alright, so yeah, now we're all good. That was worked out. We have that. And these are really just going to provide us with our y values for when eta is equal to 1, which we will use later to pretty much graph. And now, so pretty much we have these values in our array. We have the y values, we have the x values, which pretty much the x values are going to be any of the, sorry, I'm blanking on words right now. It's the distance up the Stefan tube since we scaled it from 0 to 1. So in reality, it's from 0 to 0.24 meters up the Stefan tube. But because we scaled it, it's from 0 to 1. The next thing that we will want to do is we will want to generate those values for eta from just a range of them. So what we're going to do is we're going to do plot underscore eta. And this is going to be equal to the it's going to be equal to numpy.linspace, linspace. And so what this really does is this is going to generate a array of values that are evenly spaced out, which is what linspace does. It just evenly spaces out values within an array. And so we wanted to go from 0 to 1, and we would like 51 values. So that would go through. And so, oh, don't need that parenthesis. So that will generate our x values that we will need. And then the next thing that we're going to have to do is we're going to have to go undo plot underscore mole fraction. And this is going to be equal to mole fraction dot solution. And this is going to be equal to plot underscore eta. And this is because we're using those x values that we found previously for eta from 0 to 1, and we're going to be finding the mole fractions of those values from 0 to 1 using the x values, and this is pretty much going to give us our y values that we need. And so, I just want to make sure this works. Of course it doesn't. What's new? Name mole fraction is not defined. Yes, it is. Did I mess something up here? Mole fraction was defined up here, wasn't it? Name mole fraction is not defined. So I'm not too sure exactly why that's not. Alright. So plot underscore mole fraction. Wonder. I don't think this should change anything. But I used mole fraction without an E last time, so I wonder if. I doubt that will make a difference. Worth a shot, unless I spelled it wrong. Okay. Yeah, I'm not too sure why that worked. Not actually spelling out mole. Oh, it's because I didn't use the. I don't know. I'm not going to get hung up on that, but it works now. So that's all about. So we got our values of y based on the values from eta that we were going to find from 0 to 1. And now that we have these values, we can go ahead and create our graph that we're going to use to pretty much solve the, or look at graphically to find those values over time. And so what we need to do is we need to create the figure, and in order to do this, we need to go and pretty much use this make subplots value up here. So we'll do make underscore subplots, and we're going to only need one column and one row. We don't need any more than that. And so this is pretty much going to create the graph itself, but we need to go through and actually add and just modify it really. So the next thing we need to do is fig.add underscore trace. So this will actually be adding the graph to the figure that we already kind of made. Trace is another word for graph. I don't really understand the logic behind this either, but that's how it works. So we want to go through and do go.scatter, and so this is going to be telling it that it's a scatter plot. And what we clicked out of it. And so what we need to do now is we really need to find what our x values are and what our y values are for each of the traces that we add. So the x is going to be equal to plot underscore eta, no brainer, that's our x values. And then y will be equal to plot underscored, what did I change that to? Mole fraction. And so that's pretty much just plotting our x and y values onto the actual graph itself. And we need to also identify what this graph is going to be named. And so, actually, not only this, but we need to have a look at the first value of the array, because it's only looking at the one for methanol or acetone. And so now that we have this made, we can go through and really name it. Name equals, and this is going to be acetone because that is the first value. To make sure this works. Perfect. Okay, beautiful. And so really from here, it's going to be pretty easy because we're going to take this, and I'm just going to copy and paste it to make it easier. Work smarter, not harder. We're going to create two more figurines, but the only difference here is that this one will be for methanol instead of acetone. So we'll change that. And this is going to be for air instead of either of those, the third component. And the only difference with air, and because it's the third component, and I touched on this a little bit previously above, but it's going to be, we're going to use 1 minus the value of y1 and the value of y2. And so doing this, we got to subtract from plot the mole fraction of the first array and also the values of the second array. And by doing this, we should be able to get what we want air to look like. Yep, beautiful. And so we can see here that the methanol and acetone are starting at their initial values, and as they progress up the Stefan tube, they get closer and closer and near zero, which is what they should be nearing and what they should go to, because they should not have any sort of values of that once it gets up to the screen of the Stefan tube. And inversely, we see that as these two decrease, air is actually increasing as you go up the tube, which is also expected because the mole compositions and fractions of these two are going to decrease and be replaced with air, even though it's not diffusing down. So looking at this, we're almost done here. The last thing we really need to do is just adjust the x-axis and the y-axis, well, just actually the x-axis in terms of delta, because it's still scaled currently, and to unscale it, we just need to multiply all of the x-axes by delta. Enter, and we'll run that again. And now this is showing the tube distance from what it actually is, 0 to 0.24, rather than the scaled version of 0 to 1. As once again, it's not going to change the actual values of air, acetone, or methanol, but it still reflects what we should be seeing and how it acts inversely to each other. And yeah, that's pretty much how you solve the second part of the exam. Thank you for coming.